Okay, so let's begin. So thank you for coming to our session. It's titled Big SQL Powerful SQL Optimizer Reimagined for Open Source. My name is Paul Yip. My colleague over here is Herbert Pereira. So we're from IBM. And some of you may have heard on the keynote on Tuesday about a new partnership. So there's a good chance to learn about what this really is. In particular, how we position, like, say, next to Hive, for example. This means that I'm not responsible for anything that I say. And the abstract here is really about, SQL is not new, right? There's a ton of research, decades of research that has gone into SQL optimization. And so, but up until, I guess, more recently, SQL, there's all this kind of research embodied in products that exist today, and how do we unlock that for the benefit of open source platforms like Hadoop? So that's really what this session is about our journey, what we learned, how we architected, what things we tried. And so I'm going to talk a little bit about what Big SQL is, first of all. Herbert's going to go into kind of the details of the architecture. And then I'm going to show you some kind of proof points of what we've been able to achieve with this architecture. So first off, what is Big SQL? Well, I tell customers it isn't a competitive thing to Hive. It's really an extension of Hive capabilities. It builds on a Hive foundation. In fact, Big SQL doesn't work without Hive. Okay? It shares a lot of common kind of architectural things. So when I talk to customers about Hive itself, let's think about this a little more in more detail. I see Hive as really being three things. The first is you have this thing called a SQL engine. That's runtime. That's a program you start or a jobs that get created from there. And it takes SQL that you send to it and converts it into a series of jobs, right? The runtime here is MapReduce or Tez or something else, maybe a SPARC, right? So you hear about Hive on SPARC, for example. As a separate entity, though, is the storage model. And this is the thing that's kind of evolved out of the community. You have different storage formats like ORC, Parquet, CSV, and so on. And then there's this third piece, Metastore, right? Which is when we say, what is a table in Hadoop? We look to the Metastore to tell us, oh, a table is these collection of files on these paths in HDFS, that kind of thing. And so, trying to show that Hive really is three distinct components here. Big SQL then is really this alternate SQL engine that is using a different runtime. And this is what we built, right? But it's reading over those same Hive storage formats, okay? It's reading over the same, or connecting and integrating with the same Metastore. So I'm going to show you a little quick 90-second video here to show you what I mean by this. Now, I think this is going to, there you go. I'm going to talk over it. This is let's see if it goes here. Okay, this is a terminal that I've connected to on Big SQL. And if you want to rewatch this, it's on my YouTube channel. Please subscribe. You can, is it playing? Yeah, there you go. I'm using a tool called JSquish, which is also open source. And it's basically like a beeline kind of thing, right? And I'm going to say connect to Big SQL. And from here, I'll say create Hadoop table, Paul, that's me, .test C1 integer. So that's my schema. And then from here, I'm going to load some data. So I'll just do a simple insert of 3 values, 1, 2, and 3. And then from there, I'm going to select it back to show that the data is there. Now, from here, I'm going to immediately quit. And I will do nothing else. I'll go into Hive. And this is your familiar Hive CLI. I have the debug on. You can select back from the same table. Select star from paul.test. Okay, and I get back the exact same data. The only difference is that the Hive engine was using MapReduce in this case, whereas Big SQL, I'm using our MPP engine, okay? But I had to do nothing to tell Hive about that table. That data lives as a native Hadoop format in HDFS. The table is registered in the Hive Metastore. It is synonymous for database folks. It's like I'm using Oracle one day, and I create some data loads from tables, and then, today I just don't feel like using Oracle today. I'm going to use SQL Server. But without doing anything, I'm going to use SQL Server engine to query that Oracle table space. Right? That's what makes this so interesting, is I can have different choices of SQL engines over the same data. Okay? Now, so just to summarize what you saw, Big SQL tables are Hive tables. both Big SQL and Hive see the same table, same data on disk, same definition on Metastore. And if something else better comes along, you can uninstall Big SQL. We show you a way out of Big SQL before you go in. And your data remains in open storage formats. Or maybe, for different workloads, I want to use different SQL engines over the same data. I'm going to end with that today, so stick around. This pattern is not different from things that we have already naturally evolved in the ecosystem. If you think about how SPARC uses a SQL context, Impala is very similar, Big SQL and Hive, we all have this kind of way of thinking about SQL on Hadoop. That you can have a choice of different SQL engines over the same data, all talking to that Metastore, right? Table is a table. Is this a choice of runtimes? And so I get into spiel sometimes about the truth about SQL and data warehousing on Hadoop. I actually have a paper I think will get published in TDWI. Kind of goes into this, right? Why do we exist? Especially with Hive 1 and Hive 2 is getting much better. But when I go talk to customers, and I talk to like 50, 60, 70 customers a year, both IBM and non-IBM customers, they tell us that Hive and Hadoop is decent. In fact, Hive is the thing I always fall back to when something else doesn't work, right? It might take longer sometimes, but it does get the job done. But in particular, for business intelligence workloads and for enterprise reporting workloads, stuff that I'm running on my warehouse, it's still a bit challenging to run on Hadoop, right? And I'm trying to move workloads to Hadoop, but it's really difficult or impossible to rewrite some of this stuff. It's a lot of work, right? And so when it comes to complex SQL, these could be pages long, right? That's the kind of stuff that's very challenging. And with so many options on Hadoop, where do I start? So we end up doing POC after POC after POC. And so, in fact, my day-to-day job is to track different SQL engines for Hadoop. So right now I'm tracking 15 or 16, right? And this list was longer. As a strategist, this tells me two things. The first is that there is lots of pain in the market, right? That this is a need. If there wasn't a need for something different or alternatives for different workloads, then this wouldn't exist. The second thing it tells me is that the market is very immature. They're still young. And people haven't decided yet, right? Whereas the data warehouse market is much more consolidated. And I'm sure I'm missing a few, but the point is there's lots of options, so what do we do? Well, if I think about workloads, right? We have a natural tendency to want to think about, I want one SQL engine for all my workloads. And that's a very old school data warehouse thinking, right? Because I'm going to issue an RFP, it's got 256 questions on it, and I'm going to rank you, and based on your score, that means that you're the best solution that is average at all the use cases I have, right? Right? see nods. Whereas with Hadoop, we have choices. So if you think about SQL as a language only, a specification, not a workload, and you draw circles around what the different workloads I have, you might come up with that there's different sweet spots for different SQL engines. So for example, Hive, certainly proven in large-scale ELT, large-scale queries. Now, large-scale doesn't mean complex, right? Large-scale means I pick up a lot of data, I'm going to just power through it, right? Certainly that's a strong point for Hive. But maybe I've got a lot of JSON data, and I could benefit from the syntactic candy that Drill gives me. Or maybe I want to pin that stuff in memory because I've never seen the schema before. And if I can pin that in memory, that accelerates the data that I haven't had a chance to optimize, right? Or maybe I actually have transactional workloads or lookup workloads. Maybe Phoenix makes a lot of sense, combine them with HBase, right? So when you start breaking things down in terms of workload, that SQL is a specification, not so much the solution to all things. Then we have different things. So the question is, for this circle on the left-hand side, your left-hand side, I tell my kids, this is left. If you make your L, this is left. Because this L is backwards, right? So left-hand side. Complex SQL, many users, is there an ideal solution for that? And that's kind of the solution. That's the problem set we're trying to solve. So with that, I'm going to hand over to Herbert. You want to use this clicker?
Sure, yeah.
So maybe you can introduce yourself.
Okay. So my name is Herbert Pereira, and I'm in the development team for Big SQL. I work out of the Toronto lab in Ontario, Canada. And when Paul and I were, there we go. So when Paul and I were putting together this presentation, the idea was to give you sort of a brief introduction into Big SQL. And my section was going to sort of give you an overview of the design and the architecture, and really to give you a glimpse of sort of the journey that we have been on for the past few years. When we started this journey, we had identified a gap in this space. We didn't think that there was a SQL engine that gave you SQL access on Hadoop at the enterprise level. And we thought that we could actually address that gap quite effectively. At the same time, we had a vision, and the vision was we didn't want to come into the Hadoop space with a proprietary solution that actually locked you in a specific data format and processing framework. So we wanted to provide an alternative, give you a choice to access your existing data in your data lake, for example, through a new SQL interface. And when we looked at the sort of the treasure chest that IBM has in terms of technology, there was something that immediately jumped at us. There was sort of a very good match between existing technology and the processing framework in the Hadoop ecosystem. And that was our sort of DB2 warehouse product. And this is a product very close to me because it was the first product I worked on when I joined IBM fresh off university. Several years ago, I won't tell you how many, but the processing framework of DB2, in particular the DPF, which is a data partitioning feature, matched very closely the processing frameworks in Hadoop. And the way it works is that on a DPF cluster, essentially you have hash partitioning. So we actually create hash partitions across your cluster, and those corresponds to nodes 1, 2, 3, and 4, and so on. The client issues a query, connects to a coordinating entity on a head node, and then that coordinating entity actually creates a distributed query execution plan, and it actually pushes the work to where the data resides. So we do function shipping, right? You want to do the processing as close to the data as possible, and then you're only working on each of those nodes on a subset of the data that is available. The nodes do all of the processing, and then over the network, they send the results back to that coordinating entity, and that coordinating entity does additional sorting and filtering and aggregation, and then it returns the result set, the tuples, back to the client. Now, let's move that framework over to Hadoop. And one of the fundamental differences between sort of the existing traditional RDBMSs and Hadoop is really at the storage level, right? So the challenge that we had here is that underneath we didn't have a POSIX compliant file system. We actually had HDFS, right? And the way HDFS works is that they split the data, they create replicas, so your tables are actually spread across your cluster. So how does the query work in the case of Big SQL? So similarly to our existing MPP offerings, this is the DB2 DPF, a product that I was talking about earlier. So MPP stands for Massively Parallel Processing System. And so the client connects to the Big SQL head node. And you will notice, what happened?
Move the mouse on the ground first.
Oh, there we go. Okay, so the client connects again to the head node in Big SQL, and then you'll notice a number of new components that were not there on the MPP diagram. And one of those components, the Big SQL scheduler, is fundamental. The Big SQL scheduler is really our broker into the Hadoop world. It understands Hive, it understands the name node, and it helps with the preparation and execution of the Big SQL query. So the first thing that we will do is we'll talk to the scheduler, to our broker, and this is our middle person, as I mentioned, to the Hadoop ecosystem. And then the Big SQL scheduler will figure out where the data is. It will talk to the name node. It will talk to Hive. It will apply filters. It may do partition elimination. We want to eliminate as much of the data that we need to read as possible. And then it feeds that information back to the Big SQL head node, and then the Big SQL head node creates a distributed query execution plan. And in this particular case, we're supposed to go to nodes 1 and 3 for that data. Then the work gets pushed to those nodes, and then the results come back. So one of the most fundamental phases of query execution that happens is query compilation. And this is where sort of Big SQL offers a lot of its advantages in terms of performance. And query compilation involves a number of phases, right? So on the right-hand side, I'm showing the two main components that participate in this processing. This is the Big SQL head node that I described earlier, and the Big SQL scheduler. So starting at the top, when the query comes in, we do parsing. That means syntax and error checking on the query. And we transform the query into an internal representation that the SQL engine can operate on. Then we go in, whoops. How do we go back?
Sorry, he's a Mac guy.
There we go.
We
Sorry.
don't have a clicker, so.
Oh, we don't have a clip. Okay. Then we go into the query rewrite phase. And what happens there is that folks can write very good SQL. But the IBM has years of research and field experience in terms of how to properly write a SQL query to get best performance. So we actually apply internally hundreds of query rewrite rules that actually write the query in a more efficient manner, more optimal for execution. Then we go into the phase of push-down analysis. That's where we look at the predicates and we figure out what type of data filtering we can do at what level, within what component. And then we go into the optimizer. This is where a lot of magic happens. And the optimizer runs really on two main pieces of information. One is information about the data itself that you're interested in. Those are statistics, right? Give the metadata about the data. And then it has information about the computing power that you have in your cluster. For example, what sort of CPUs you have, configuration, network bandwidth, so on and so forth. And the optimizer then looks at a number of different possibilities in terms of how to most effectively execute your query going after that specific set of data at this particular point in time in your cluster. So the optimizer will go and pick the most optimal plan. And then we generate the executable code. And if you actually want to look at what your query looks like at the end of this processing, there are explain tables that will describe the actual query that gets executed. So this is another sort of graphical description of what happens and in more detail. Again, we have a head node on the left and the worker node on the right. The client connects. There's a coordinating entity on the head node. This is very important. One of the first things that the coordinating entity will do is actually it will talk to BigSQL's own metastore. So in our BigSQL solution, the way we describe it is that we have an augmented metastore. So we actually use both the Hive metastore, but there's additional metadata that we maintain ourselves in our own metastore called the BigSQL catalog. We may have to go to the Hive metastore as well, and that may happen. And then we move into the phase of building that query execution plan. So we go through the compilation and optimization phases I described. Then we go into the runtime engine for query execution. And then at that point, we build this distributed query plan. We know what nodes we need to go after, and we send that work over to the worker node. The worker nodes implement a stack that is very similar to that of the head node. And there's a runtime engine as well. One of the things that the worker nodes may do is actually temp some of that data, right? So we will use the local file system on the worker nodes and database infrastructure and buffer pools to allow you to allow us to do that temping very effectively. And then we get into one of the most interesting phases of the query execution. This is when we do projection, selection, and we actually want to run the scan on that particular node. And we do this through these entities called HDFS readers. And these guys are important because this is in keeping with our original strategy of really not locking the user into a specific data format or processing framework. So what we've actually done is created an I/O interface with open source components that allow things to do, like, for example, you can read Parquet data, you can read ORC, or your own custom formats as long as you provide a SERDI. And then what happens inside those readers, where there's a process of scanning for the data, reading the data, and a process of transformation. And transformation really means taking the data in its original format and transforming it in a format that is consumable within the SQL engine. Then at that point, we can complete the scan, and actually the rows start flowing back into the runtime execution. There's additional processing that happens. We may have to apply additional predicates in that case, and then the result set is flown back to the coordinating entity. And this brings it all together, right? So here on the upper left-hand side, you have the management node running the BigSQL node and the BigSQL scheduler component. And then on the right-hand side, you have the Hive and the Hive metastore, and then the worker nodes underneath. And you'll see the blue boxes. Those are our native, the I/O engines. And we offer, as I said, a native, we call it a native I/O that supports Parquet format. And then we have a Java infrastructure for ORC and various other formats. Now, let me go back to that point about the augmented metastore, because it is important. You will ask, well, you actually have two metastores then in your system. How do you keep them in sync? And the mechanism that we have, and this was released in our previous release, it's actually a mechanism where we actually catch events in the Hive metastore. And then we have a consumer infrastructure on the BigSQL side that actually monitors and consumes the events. For example, DDL changes that you're driving into your Hive. And then we provide an interface where the user can say, well, listen, I have done some work on, through Hive, right? And I know that the metadata on the Big SQL side may be out of sync. So we actually, through the embodied interface, provide you a mechanism by which you can actually sync the two of them, right? We also, and we introduced that in a last release, is the ability for the user to not have to worry about this at all. And you can actually enable automatic synchronization. We call it HCAT sync, automatic synchronization of the two catalogs. Analyze. So going back to the statement I made about statistics, I view this as a rocket fuel to the optimizer, right? The quality of the query execution plan really ties to the quality of the statistics. And the first sort of statistics gathering infrastructure that we implemented in Big SQL was based on the analyze statement from Hive, and it was built on a MapReduce framework. One of the things that we immediately ran into was that it had sort of scalability and performance challenges, especially with the size of workloads that we were trying to tackle and the size of the data. So we actually went ahead and implemented, we used our own MPP engine in Big SQL to implement a version 2, we call it, of Analyze, which actually does all of the in-memory processing, and it uses Big SQL to go and gather and process and aggregate the statistics. And what we determined was that this gave us up to 11 times faster performance than version 1. And this is an area that we continue to invest in. Who knows, we may look at SPARC next as a mechanism for statistics gathering and processing. And some highlights of the analyze statement in Big SQL, so you can specify all columns or some of the columns. We support cumulative statistics. We also support, and this is very important, especially when you get into sort of the petabyte size of your data set, is system sampling. So you can actually collect stats. If you're going to collect comprehensive stats on petabytes of data, it's going to take you some time, right? So we actually allow you to do it on a fraction of that data through the sampling support. And we also introduce the ability for Analyze to run really more than automatically is autonomically. And what I mean by that is that Analyze is smart enough to figure out when statistics are needed, right? Whether, for example, your query is referencing a table that doesn't have stats, or there's been a change in the size of the table significant enough that warrants collecting stats, or you've done a load of new data, or there's been a synchronization run against the Hive, and all of this is highly configurable. And this is a sort of a graphical description of what we leverage to be able to do this administrative operations. So both the auto HCAT sync and the auto analyze rely on this thing called the admin task scheduler, which allows you to schedule administrative tasks against Big SQL so that those get run asynchronously from your primary user workload without impacting it, right? And it will collect the data and do whatever processing is necessary. We rely heavily on this for various other operations. So this is all about Hive, right? How about other storage models and sort of processing frameworks? So one of the other storage models that we went after was HBase. And essentially, you can create Big SQL tables against HBase. And I'm not going to spend too much time on this, but this just shows you the syntax that you need to be able to, very straightforward, to be able to create an HBase table, a Big SQL table on HBase, right? And important to note is the encoding. Our default encoding for Big SQL is binary encoding. And then there are salting and column mapping options that, again, are specific to Big SQL. And because they're specific to Big SQL, some of the, for example, Kafka and Flume connectors out there did not support it natively. So in our latest release, we've actually made the changes into these connectors so that they fully support these options on Big SQL. Let me touch briefly now on Object Store. So this is something else that is available in our upcoming release, which is the ability for you to perform SQL against tables that are created in Object Store. And the beauty of this is that it's very simple. You define your table, and you point in the table definition, you specify that the data resides in an Object Store, and then all of your SQL applications and SQL statements will work transparently with that table, as if they were Hive local tables. There's no distinction or differentiation that needs to be done in your SQL. Internally, obviously, there are some differences because our optimizer, for example, will know that this data is remote, and it will pick a different plan for execution. And our load facility, this is what I'm showing on the cloud here on the lower right-hand side, is fully integrated to support the Object Store. We've also released, this is in tech preview right now, the ability to, again, create tables over a web HDFS interface. And this is pretty powerful because this allows BigSQL to actually access data that resides on a remote data lake or on any web HDFS-enabled storage. And the one sort of consideration, and we're doing heavy testing in this area right now, is really performance, right? When your data is remote, you're reliant on the network for being able to move the data back and forth. So that's one of the considerations you need to keep in mind. The other area where we've done significant work is in SPARC. I mean, here you have two great technologies, frameworks for processing, and we thought, well, wouldn't it be great to actually, instead of forcing customers to make a choice, how about we bring them together into the same offering and into BigSQL? And really what we offer is the ability to run SPARC jobs as slave SPARC applications within your BigSQL queries, right? And then this allows for data and control flow to happen in parallel, and even the local data transfer happens on the worker nodes in parallel. And the way this works is very simple. Here's a select statement where you're actually referencing a table, which happens to be a SPARC job, and here we're accessing a JSON document. We don't know the structure of the JSON document ahead of time. So this, in our view, brings the best of SPARC into BigSQL. And you can imagine sort of the number of applications that this allows you to pursue now. You can do machine learning, custom analytics, schema on read. And because SPARC has a rich library of connectors, you're actually able to access data in storage that our federation capabilities may not currently support. And in terms of the integration aspects, worth highlighting that we support actually both. You can actually run a SPARC application from your SQL query, or you can run actually a BigSQL query from a SPARC application. So if you're writing a SPARC application and you think this is particular complex analytics workload where BigSQL could help me, you can actually run that query directly from your SPARC application. As I mentioned earlier, kind of our strategy was to come into the Hadoop ecosystem and integrate with the rest of the components in an amicably fashion, right? And part of that was starting with our 4.0 release and our support for the ODPI standard. We changed the installer to run through Ambari. And I'm going to go very quickly over this slide. This just shows the Ambari installation. In BigSQL, there are two components. Highlighted is the BigSQL head component, and then you have your worker components. There are all sorts of customization parameters and input parameters. This is the installation in progress. And this is what sort of the final Ambari page looks like for administration. And as you see, there are all sorts of options and configurations. And one of the things that I'm actually quite concerned about is really the size of our service actions. I mean, that menu is growing in size. When you have services like BigSQL, very rich in functionality. Now, with this closer collaboration that we'll have with the Hortonworks team, I'm looking forward to figuring out with them, a better interface to make this more usable. I don't want to end up with 4 or 5 pages of service actions on the right in a future release, because that's the way we're going. And in terms of features, so we, in this latest release as well, we're announcing integration with Ranger. Right now, the integration is done through what I call the external faceable components of BigSQL. This includes the scheduler and as well as the I/O engine. But something that I'm very excited about, what we're actually working on right now, and our developers have sent out the code for review to our committers, and the design and the code is actually we're opening up DB2 so that it can actually invoke Ranger authorization APIs or any other system that you want to use for authorization from operations that happen internally in the DB2 infrastructure, such as views and store procedures and so on. Last but not least, I wanted to touch on our integration with Yarn. This is something that has been in tech preview with BigSQL for some time, and it's been the result of sort of a couple of limitations that we had. One was on our end that we did not, and this was a design decision, not an architectural decision, but we did not want to run multiple containers of BigSQL on the same host. And then there were some JIRAs that we were dependent on, especially there was an issue with C groups on Red Hat that we were waiting for. That got resolved last year, and then we went ahead and now completed the integration. And this is just a graphical description of how it works. So probably the most important component in this picture is that red box. And that red box is really the BigSQL's implementation of the slider package. We use slider. I remember in conversations with Hortonworks a couple of years ago, this is what they recommended for long-running services like HBase, and we fully embraced it in BigSQL. So what happens is the Big SQL will deploy a Big SQL application manager on the node managers, and then that interface is used to starting up and shutting down the various Big SQL workers. So this is, Slider is used for long-running services that don't implement Yarn natively. And we also support the Flex interface of Slider, so it allows you to actually stop some of that capacity if you don't need it, and then it gets released back to other consumers in Yarn. One of the other features, and I'm going to go quickly, that we're making available in this latest release is what we call the Elastic Boost capability. And this goes back to what I was saying about being able to run multiple containers of Big SQL on the same host. So really what this maps to is that instead of running one container, using the same configuration, you can run multiple, right? And why is this important? It is important because one of the, when you look at Big SQL and some of its components, when the compiler and the optimizer actually builds a query execution plan, it builds the most optimal it can, right? And that may lead that if you're running a single query, it may not consume necessarily all of the CPU resources that you have available on the machine. So we've had scenarios where customers say, you know, I'm running my query, but I think it can run faster because you're only consuming 75% of the CPU that I've given Big SQL. Well, the fact remains that is the most optimal plan for execution, and that's what Big SQL will run. If you really want to tap into that additional capacity that you have on your system, start running multiple streams of that query. That's what Big SQL was built for, to run dozens, hundreds of these queries concurrently. And then you'll see Big SQL consuming all of the capacity that has been given. Another way of doing it is through this concept of multiple containers on the same host. And this is just an example of going from a single container to 4. It actually improves your performance by about 40%. For the sake of time, and so that we leave some time for questions, I was going to give it back to you. So, okay? So you'll have to skip the next set of slides.
I'll end on this. If we're going to use Yarn to delegate where we're going to start workers, and we can just, kind of boost up and boost down, what does 50% mean? This is what we typically think about. It could look like this. It could look like this. So just I guess a footer note, okay? So you heard a lot. You just heard a massive brain dump from one of our smartest guys in the lab. And what I wanted to show you was, what can we do with this stuff? How does this stuff prove itself out in workloads? So here's a performance study. The workload we chose was an industry open standard called TP-CDS. And you're seeing more and more of these. It wasn't so common 2 years ago. It certainly is now. Everyone's talking about how they can run TP-CDS queries. This is different from TP-CH. TP-CDS, much more challenging. Now, from a perspective of what's in TP-CDS, is a kit that you can get. And you can build this model of data, and there's different scale factors from 100 gigabyte all the way to 100 terabyte. It's got 4 classes of queries: reporting, iterative, data mining, ad hoc, and these 99 predefined queries and a set of rules for what you're allowed to do with those queries. You're allowed minor tweaks to the queries, but certainly they're looking to exercise the capability of the SQL engine. We want business users to express what they want to ask as a question, not think about how it should be run on the system. So those are the rules. Now, we chose this because a lot of people are trying to move workloads from warehousing into Hadoop, right? And for over a decade, all the big vendors in data warehousing competed on this benchmark: IBM, Teradata, Oracle, so on, right? So if this is what we use to prove our wares, and you're thinking of moving some of these workloads to Hadoop, then it makes sense for us to see how this workload runs on Hadoop. Fair? So, actually, the previous world record we set back in 2014. We kind of threw the gauntlet down, and we said, we ran this workload for Big SQL, and we ran it at 10 terabyte scale, which is and 30 terabyte scale. That was the previous world records. And that was 2014. What was special about this was not only did we run it, we decided to go get it audited by a certified TPC auditor. So this thing you see on the left is the letter of attestation that we ran it according to the rules, and we had full disclosure of how we ran it. So I'm going to show you 2 examples of this running so you can kind of understand where this technology really shows itself off. So SPARC 2.x runs all 99 queries. And part of this is because of IBM's SPARC contributions. As you may or may not know, we have the SPARC Technology Center. We were the #2 contributor to SPARC 2.0, second only to Databricks. And we were very focused on where we're actually contributing. You see one of the areas is SQL and ML. And we also know that we could run all 99 queries at lower scale factors. And when we did this seminar back at SPARC Summit late last year, we found that we could get very close. We can technically run all the queries, but when we got to this larger scale, 2 would still fail. So there are 2 pieces. The first is compiling. Can I compile the query? And Herbert talked about compiling, right? The second is, can I run it? Which is a different thing. There's 2 factors. Now, when 2.1 came out, and there were hundreds of fixes that went in 2.1, we asked, what would it take to run a 100 terabyte scale, which is the highest scale factor of this? And so this was with the SPARC Technology Center, and we worked with our partners at Intel. I'll talk about that in a little bit. But this is big data. It's 550 billion rows. It's got fact-to-fact joins, lots of tables, and we use Parquet format. So we worked with our partners at Intel and Lenovo, and they're showing off their wares and Mellanox. And we came up with the system. We call it the F1 cluster. 28 nodes, 18 cores per socket, 1.5 terabytes of RAM, racked with SSDs, 100 gigabit E-switch. So a pretty powerful box, right? So from the hardware vendor's perspective, because stuff is licensed per node, of course, they want to show off how much they can fit on a very small footprint. And so this is with the SSD, because SPARC is very memory hungry, that will support that as well. And this was the result. You can see the number drops again, right? So from I can run all 99 at lower scale to 97 at 10 terabytes. And now as we hit 100 terabytes with a highly engineered machine, we're still, the best we could do was 83. And these are with the best people in SPARC that we have. But we're fairly confident that this is a very good result, because if you look at what other SQL engines are doing, they're not hitting this number. This is the very high number in terms of query capability. It took about 2 days to run. We're fairly satisfied that, in the SPARC environment, that we used all the CPU memory available, right? But my next question is it a good result, right? And the reason I ask this is because we don't really know if it's a good result if we can't compare it to anything, fair? Well, the good news is, if you remember what I said earlier, is that we did run this back in 2014. So Big SQL also runs all the TPCS queries. So we talked to the SPARC guys, said, hey, can we get some time on that machine? That's a really cool machine, right? We didn't have time to regenerate the data. We used the exact same data sets they used, because it takes over 40 hours to generate the 100 terabyte data set, even on SSDs. So we used the same storage. We just threw Big SQL on the same machine, and I'm going to show you our results. So the teaser is, of course, I'm going to say it's faster. I'm going to take you through why. We talked a lot about optimizers and runtime. So we know that with SPARC, we went from 1 to 1 terabyte. As we get to a higher scale, the more challenging queries start to have challenges. But when we ran it, we were able to get all 99 queries running at all scale factors. That's the first interesting point. Okay. From there, we looked at CPU utilization. How well did we run it, right? And you can see here that SPARC, they're both running at 74 user CPU utilization on average. But look at the system. The system CPU actually is what we internally call kind of wasted CPU cycles, because that's the overhead to manage our processes, our runtime. It doesn't actually achieve anything. It doesn't move the ball forward, right? So there's opportunity to optimize there on the SPARC side. We're fairly well tuned there at 5%. That's very, very healthy. From there, we looked at I/O. Now, it turns out that with SPARC, when we compared the average I/O rates megabytes per second, SPARC was using 3.6 times more reads and 9.5 times more writes for the very same workload. We thought this is all optimizer, right? Because this is about, I'm not relying on in-memory processing. I'm trying to reduce the amount of data I'm reading from disk to begin with in the first place, right? The second thing we noticed was when we are asked to drive I/O with that multiple logical work technology we talked about, driving I/O, we're actually able to drive 2 times more, almost 2 times more I/O for the same workload. So this is the result, right? It turns out we're about 3.2 times faster than SPARC on this workload. So you go, why is the number not higher? Because we read so much more data than SPARC. Well, we saw very little latency on the SSDs. The SSD was powering the SPARC workload. So, had this been regular spinning disk, this number probably would be bigger, but still, very good showing here. And this is comparing the 83 queries that they could both run. On the final set of 99, we were still comparing 99 queries to the 83 we could run on SPARC. It was still 2 times faster. So I want to end with some math. You saw this picture, right? And you saw that it was 75% CPU roughly. But remember that this side ran 3 times longer, right? So actually, this is 3 times more CPU time for the same workload. On this picture here, you saw that the average I/O rates, but remember that workload ran 3 times longer. This is an average per second. So actually, when you factor in the math, it's actually reading 12 times more data and writing 30 times more over the same workload. And the best part here is that there's a lot of potential, because remember that memory picture that I showed you? We did that with 1/3 the memory of what was available in the system. And this was really telling for us. This means that you could configure boxes with less memory, because these were very high memory boxes. Or maybe this frees up a ton of memory for your other jobs that also need containers. So anyway, this is a kind of the wrap-up of what we did. We got lots of happy customers, especially with BI workloads. This is Manhattan Associates. They've got a quote here from the director. If you're using Cognos, BigSQL is the best option for Hadoop. Data Medica loves our product. They think big SQLs are big data's best kept secret. And I just want to comment on the relationship real quick. This is the last slide, I promise. This relationship between Hortonworks and IBM, we're combining DSX and BigSQL with the best open source platform for Hadoop. So I think it's great for us, great for our customers, great for Hortonworks. So I'm going to stop there. Any questions? BigSQL is not open source, good question, but we've tried to show you that we're integrating in every possible way with open source, Ranger, the scheduler, all that kind of stuff, and we show you the way out of BigSQL. For a lot of reasons, we can't open source that piece, but you're not locked in. That was the point. Yeah. Okay, so we're at time. Yeah, if you want to come and talk to us afterwards, thank you very much for your time.